The normal distribution. One particularly important class of density curve is the class of normal curves, which describes normal distribution. And all normal curves are symmetric, single-peaked, and bell-shaped. A specific normal curve is described by giving its mean mu and standard deviation sigma. Sigma is the standard deviation. What is the width of this curve? This is described by this sigma. So a normal curve could look like this or could look like this depending upon the sigma, but they both are the normal curves. So a normal distribution is described by a normal density curve, and any particular normal distribution is completely specified by two numbers. Its mean mu and standard deviation sigma. The mean of normal distribution is the center of symmetric normal curve, and standard deviation is the distance from the center to the change of curvature points on either side. And we abbreviated the normal distribution with mean mu and standard deviation sigma as. We have to remember this thing. You will see many times there is written n, and in the parenthesis it's saying mu comma sigma. So it's telling you that the distribution is normal with mean mu and standard deviation sigma. Here could be the values like mean 0 or standard deviation 1, mean 3 or standard deviation 2. Anything could be there. So this is a particular symbol for normal distribution. So we are here now 68, 95, 99.7 rule, and it's also known as 3 sigma rule. So here in the normal distribution with mean mu and standard deviation sigma, approximately 68% of observation fall within sigma of mu, whereas 95% of the observation fall within 2 sigma of mu, and 99.7% of the observation fall within 3 sigma of mu. That is, from here to this, from -3 to 3, all the observation, that is the 99.7% of the observation, will be from -3 to 3 if the distribution is normal. So we will understand this from -1 to 1, it is 68%. -2 to 2, it is 95%. So if we want to know from -2 to -1, then we already know that this is 68%. So what we can do, 95 minus 68, and what the value we will get almost, we'll get 27, and then we can divide it by 2. So because these both are equal, so this is almost like 13.5 or 6% observations will lie in this region. So one should memorize these numbers, but we will use again and again, so you will memorize it later. So here's the example with the 3 sigma rule, and here we can see the distribution of ITBS vocabulary score for 7th grade students in Gary, Indiana is close to normal, and suppose this distribution is n with mean 6.84 and standard deviation 1.55. And we have to sketch the normal density curve for this distribution, and what percent of ITBS vocabulary score is less than 3.74, and what percent of the score is in between 5.29 and 9.94. So we will go one by one. First, because we know this is the 3 sigma rule, so we will make a symmetric curve, and we can see mean is 6.84 with we are increasing it with 1.55. So we can see here when we are going from here plus 1 sigma, then we are getting these values, and here we are subtracting with 1 sigma. So we can make it like this, and then it's asking about what percent of ITBS vocabulary score is less than 3.74. Where it's 3.74, it's here. So it's asking what, how much percentage is this who are getting less than 3.74. So how we will get it from 3 sigma? So we already know that this area, the total area is always 1, that is 100%. So for the 100%, we already know that this is 95%, because it is covering 2 sigma from 3.74 to 9.94. So this is the 95%. So how much is left? 5%. And because this is only in this tail, that is the half of the tail, then we will divide it by 2. So 5 divided by 2 is 2.5%. Now we can understand it's 2.5% of the scores are less than 3.74. Now it's asking about what percent of score is in between 5.29 and 9.94. So here we can see that it is from asking from, because mean is 6.84, 5.29 to 9.94. So this is the 68%, and if you are taking the example from 2 sigma from here to here, it would be 95%, but we are not considering this part. So what it is doing, 95 minus 68% divided by 2, that is 13.5%. So we will subtract 13.5% from 95%, and we will get the percentage of the scores between 5.29 to 9.94. So we have to standardize the observation. So here we are talking about if a variable x has distribution with mean mu and standard deviation sigma, then standardized value of x or its z-score is x minus mu divided by sigma. So this is a very important concept, z-score. So we will understand it. So all normal distribution are same if we measure in units of size sigma from the mean mu as center. And the standard normal distribution is the normal distribution. We were learning about normal distribution, and now here we are talking about the standard normal distribution. And in the standard normal distribution, we always have mean 0 and standard deviation as 1. And how we represent it, here we can see the representation. It is n parenthesis 0 comma 1. 0 is the mean and 1 is the standard deviation, and this looks something like this. So here we can see this is the mean and these are the standard deviations going from there. So we will go from here. So because all normal distribution are the same, when we standardize it, we can find areas under any normal curve from a single table. So here are the values we can see here, and this is a table of areas under the standard normal curve, and the table entry of each value z is the area under the curve to the left of z. So there are normally two different z tables. One is for the left and one is for the right. So here is the example of the under the curve to the left of z. So here we can see if we have a z value minus 3.42, so we will go for minus 3.42. So it would be minus 0.003. So although these all are same, but when they are not much same, like here it's minus 2.61, then it would be 0.0045, and then it's decreasing. So these values we can get from z table. So here is the again we are getting, this is an example, standard normal table z. Entries in the table give the area under the curve between the mean and z standard deviation above the mean. So for example, it's saying z is equal to 1.25. The area under the curve between mean 0 and z is 0.3944. So how would we calculate it? So we will go to 1.2 and then fifth value. So this is this one. So it's 0.3944. And here we can see what from where we got our 68, 95, 97, 99.7 rule. So here we can see here this is 1 and the value is 0.3413. So when we will, because this is only from of one side, so when we take both sides it would be 0.68, that is the 68%. Similarly, when we go to 2, it's showing 0.4772. So it would be almost 95%. And similarly for 3, we can calculate it. So here's the one more example, and here is the example. We want to find the proportion of observation from the standard normal distribution that are less than 0.81. And now we can use table A for that, and it's saying 0.81. So it's 0.8 and 1. So it would be 0.7910. So here we can see that we have to find the proportion of observation from the standard normal distribution that are between minus 1.25 and 0.81. So we can do area to left of z 0.81 is 0.7910. We can see here 0.81 is 0.7910. And then we can, because we have to understand it, less than 1, it's 0.81, and this is the less than table. So we are getting 0.81 value, that is the left part, it's 0.7910. So to get the this part, what we will do, we will subtract it to 1 from 1. So it would be 1 minus 0.7910. So what would be the value? It would be 0.2090. So now we will go to z value of minus 1.25, that is 0.1056. And if we have to find the area in between the minus 1.25 and z 0.81, then we are getting it by subtracting 0.791 minus 0.1056, 0.6854. So we can use different approach for this too. And here, what's that? Here, if we have to find this value, so what we can do, we can get the area to the left of z of minus 1.25, that is um, 0.1056, and the area to the right of the z of 0.01, that is 0.2090. So then what we can do, we will subtract it with 1. So 1 minus 0.1056, and this area we are not taking into consideration is plus 0.2090, that would be equal to 0.6854. So how to solve problems involving normal distribution? So first express the problem in terms of the observed variable x, and then we have to draw a picture of the distribution, shade the area of interest under the curve, and then we have to perform calculations. Standardize x to restate the problem in terms of a standard normal variable c, and use table A and the fact that the total area under the curve is 1 to find the required area under the standard normal curve. So I will also attach the Z table in Blackboard, so you will be able to calculate from it, or you can also use online calculator. So it would be better to understand. So here's our next example. It's saying according to Health and Nutrition Examination Study of 1976 to 1980, the heights in inches of adult men aged 18 to 24 are with normal distribution mean 70 and standard deviation 2.8. And if exactly 10% of men aged 18 to 24 are shorter than a particular man, how tall is he? So for this, we will calculate. So here we can see now we have to do the opposite thing. First we were taking the z values and seeing the getting the p values from it, but now it's giving you the under area p value, and now we have to get the z score of that. So for what we will do, we will do what is nearest to 0.10. So I think the nearest one is minus 1.2. It's minus 0.1003. That is minus 1.28. So now we have value of z, that is minus 1.28, and we need to unstandardize the z-score to find the observed value x. So for that, already we know the formula of z is equal to x minus mu divided by sigma. So to get the value of x, what would be the formula? It's x is equal to mu plus z sigma. So we will put all the values here. That is x is equal to 70 plus z multiplied by 2.8. So we already know it's minus 1.28, and after doing all the calculation we got 66.42. So we got our answer that a man would have to be approximately 66.42 inches tall or less to be in the lower 10% of all men in the population. So uh, one way to assess if a distribution is indeed approximately normal is to plot the data on a normal quantile plot. So we will understand it. So the data points are ranked and the percentile ranks are converted to z-score with table A. The z-scores are then used for the x-axis against which the data are plotted on the y-axis of the normal quantile plot. If the distribution is indeed normal, the plot will show a straight line, and this indicates a good match between the data and a normal distribution. And systematic deviation from a straight line indicate a non-normal distribution, and outliers appears as points that are far away from the overall pattern of the plot. So here in the graph, we can see this is the straight line where this is the curved one. So this is showing, the straight one is showing the distribution of rainwater is close to normal, whereas this curved pattern is showing that the data are right skewed and few individuals have particularly long survival times. So normal quantile plots are complex to do by hand, but there are standard features in most statistical softwares, so we don't need it to do by hand. So I hope you learned a lot from this chapter, and we will check back for chapter 2 again.